Now, we would like to find out the scattering matrix and the properties of the Fabry-Perot interferometer, which is also called Fabry-Perot echelon. The Fabry-Perot interferometer is formed by two partially transmitting mirrors, mirror 1 and mirror 2. These two mirrors are separated by a distance L. Between these two mirrors, there are material of index n. The scattering matrix of the mirror 1 is S1, which is written in this way. And the scattering matrix of mirror 2 is written as this. At pole 1, we have input A1, and we suppose that at pole 2 there is no input, so A2 is 0. And we start from the amplitude of the input wave A1. And A1 will have the first reflected wave here. According to the scattering matrix of mirror 1, we say the amplitude of the first reflected wave is minus R1 A1. And at mirror 1, the first transmitted wave amplitude is JT1 A1. This light beam will propagate from mirror 1 to mirror 2 at this point. Along this path, it will gain phase difference exponential minus j half delta. Here, half delta can be obtained by omega n over c times L cosine theta. Okay? And then this light beam will be reflected by mirror 2, and the amplitude will become minus R2 times the original amplitude here. This light beam again propagate from mirror 2 to mirror 1, and the amplitude will gain another phase difference exponential minus j delta. So the total phase difference will become exponential minus j delta. This light beam at this point is reflected by mirror 2, so the amplitude can be obtained by multiplying the original amplitude with minus R1. So you see the amplitude will become R1, R2, JT1, A1 exponential minus J delta. And this light beam again goes from mirror 1 to mirror 2, reflected by mirror 2 goes from mirror 2 to mirror 1, and again. The total system can be reported in this way. We have mirror 1 here with the corresponding scattering matrix S1. And we also have mirror 2 here with the corresponding scattering matrix S2. At pole 1, we have input A1 and output B1. At pole 2, we have input A2, which is set to be 0, and output B2. Between these two mirrors, we have a lot of light beam goes from mirror 1 to mirror 2. So all the light beam goes from mirror 1 to mirror 2. We call it A. And this light beam will be reflected by mirror 2, and again goes from mirror 2 to mirror 1. As they arrive mirror 1, the amplitude is set to be B. Okay, so B is all the light beam go from mirror 2 to mirror 1. Our purpose is to find out the scattering matrix of the whole system, which will help us to express B is B1, B2. They are S11, S12, S21, S22 times A. Letter is B is SA. So our purpose is to find out all the elements in the scattering matrix for the whole system for the Fabry-Pérot interferometer formed by the two mirrors. Okay? First, let's consider what will be the amplitude of A. As I have said, A here is the amplitude of all the light beams goes from mirror 1 to mirror 2. So for the first one, the amplitude will be JT1A1. And for the second one, it will be R1 times R2 times exponential J minus J delta times JT1A1. And you can easily to find out the third term to be R1, R2 exponential minus J delta, the square of the total one, times JT1A1, right? And also you can find out the other higher order terms. And according to the rule of each term, you can find out A to be the summation of each term. And it can be expressed as JT1A1 divided by 1 minus R1 R2 exponential minus J delta. Okay? By performing the summation of each term of each amplitude goes from mirror 1 to mirror 2, you can have the amplitude of A to be in this form. How about B? As I have said, the amplitude of B means A goes from S1 or goes from mirror 1 to mirror 2 and reflected by mirror 2 and goes from mirror 2 to mirror 1. Then we have B. So the amplitude B can be obtained by start with A. Goes from mirror 1 to mirror 2, you will gain phase difference minus J half delta. Reflected by mirror 2, you will have the original one times minus R2. And along this path, you will gain another phase difference minus J half delta. So clearly, the B can be expressed as A times minus R2 times exponential minus J delta. Okay? Again, the whole system of the Fabry-Pérot interferometer is plotted in this way. For mirror 1 here, we have the scattering matrix S1 to be minus R1 JT1 minus R1. At pole 1, we have A1, B1. At pole 2, we have A2, B2, where A2 is 0. Our purpose is to find out the scattering matrix of the total system. And from the definition, we know that B1 it will be S11A1 plus S12A2. And the B2 can be obtained by S21A1 plus S22A2. And using the scattering matrix for the mirror 1 here, and we have the corresponding input-output at both sides. You can say that B1 can be expressed as minus R1A1 plus JT1 times B. And A can be written as JT1A1 minus R1B. And from these two equations, you can easily obtain that B1 can be written in this way. Okay? And according to this equation, we know that if A2 is 0, B1 will be S11A1 as A2 is 0. And this result is obtained by setting A2 is 0, right? So we can say this one will be S11. This one will be S11. And what is B2? Clearly, B2 here can be obtained from A. A goes from mirror 1 to mirror 2 and transmitted, it will become B2. So we start from A, goes from mirror 1 to mirror 2, it will gain phase difference exponential minus J half delta, and then times the transmission coefficient for mirror 2. According to the value of A in previous slide, you can have B2 expressed as and of course, here B2 is obtained as A2 is 0. So according to this equation, as A2 is 0, B2 can also be written as S21A1 as A2 is 0. So you can say this term will be S21. Following, according to the above result, you have obtained S11 and you also have obtained S21. And due to the scattering matrix S is symmetry, we know that S12 will be the same as S21. So the four elements in the scattering matrix of the whole system, we have already obtained S11, S12, and S21. Now we like to obtain the value of the expression of S22. How to find out S22? As you can see, by setting A2 is 0, we can obtain S11. So if you want to obtain S22, you can use the inverse process. That is, you set A1 to be 0, and following the same process, you will have S22 here. So following the process finding out S11, you can just interchange 1 with 2, then you will obtain the result for S22. Finally, we have we have the scattering matrix of the whole system of the Fabry-Pérot interferometer to be written in this way. And you can see S12 is the same as S21, and you can obtain S22 by interchange 1 and 2 in S11. Then you will have S22 here. So this is the total scattering matrix of the whole system for the Fabry-Pérot interferometer.